Okay, so now we're going to discuss ionic and covalent bonding. So in chemistry, there are two basic kinds of bonding. There's ionic bonding and then there's covalent bonding. So here's an example of ionic bonding. So what we have here is we have what we want in ionic bonding. Actually, in all bonding, we want to have the noble gas configuration or the full valence shell as your final atom structure. So you want to end up with a noble gas configuration. So what we're going to do here is we have lithium here that has 1 valence electron. We have fluorine here that has 7 valence electrons. So this does not have an octet. This also does not have an octet. So what we're going to do in ionic bonding, and ionic bonding is between two elements on opposite side of the periodic table. So you'll see that lithium is on the extreme left of the periodic table. It's in group 1. Fluorine is in the extreme right of the periodic table. It is in group 7. So they're on opposite sides of the periodic table. So it's between a metal and a non-metal, between two elements on opposite sides of the periodic table. So we have 1 electron here and you have 7 electrons here. We would like to have an octet. So how are we going to get an octet? Well, we're going to donate the electron from the lithium and give it to the fluorine. So our lithium is going to lose its electron, and now we end up with a lithium that has the electron configuration of helium. So when we got rid of that last electron, you actually go down 1 energy level. So you go down 1 principal quantum number down to a lower period of the periodic table. And now we have the noble gas configuration of helium. It actually is a full valence shell. It's just not the outer shell that you originally started off with. We also have the neon configuration for the electron configuration for fluorine, because now it has gained an electron. It took the electron from the lithium, so now it also has an octet. It now has the electron configuration for neon. It has an octet. It has a full valence shell. It is the electron configuration of a noble gas. But now you also have a positive charge on this lithium and a negative charge on that fluorine. So then you form an ionic bond. So this is my ionic bond. An ionic bond is an electrostatic interaction between the positively charged lithium and the negatively charged fluorine. So what about covalent bonding? So here's an example of covalent bonding. So in covalent bonding, and covalent bonding is the bonding that you have in almost all organic molecules. So after this first few chapters, we're just basically going to only deal with covalent bonding almost exclusively. So in covalent bonding, we also want to end up with a noble gas configuration. We would like to have a full valence shell. So we want to end up with an octet in our final structure. So, but what we're going to do in covalent bonding is we're actually going to share electrons rather than just taking an electron away from the other atom. So we have a fluorine. Once again, it has 7 electrons in its valence shell. We have the other fluorine. It also has 7 electrons in its outermost shell. Neither of them are full valence shell. Neither of them are noble gas configurations. Neither of them are octets. So now what we're going to do is we're going to try to share that electron from one fluorine with the electron from the other fluorine. So both atoms are now going to share 1 electron from the other atom. So now we have an octet around both atoms. So both atoms are neutral. So this is not an electrostatic interaction. This is an interaction where you actually share electrons between the two atoms. So this is my covalent bonding. Okay, so what about Lewis symbols? Well, the way you can write Lewis symbols, it's actually pretty straightforward. So carbon is in group 4. Nitrogen is in group 5. So this is in group 4. So carbon has 4 valence electrons. Nitrogen is in group, I can't really write really well with this little pointer. So nitrogen is in group 5 if you look at the periodic table. So how many valence electrons does it have? It has 5 valence electrons. So I actually show the 5 valence electrons by showing the little dots around the atom. So here we are in group 4. We have 4 valence electrons. I show the 4 valence electrons. And the way I do this is when you're doing Lewis symbols, you think of 4 walls around the atom. And then on each of the walls you put a single electron until you run out of the 4th wall, and then you start doubling up. So I have 1 electron on each of the 4 walls because carbon is in group 4 and it has 4 valence electrons. Nitrogen is in group 5, so it has 5 valence electrons. So I'm going to put 5 dots around the nitrogen symbol, and I'm going to put them in the order where you have 4 walls. 4 walls. So you put in your first electron here, your second electron goes here, your third electron goes here, your 4th electron goes here. Your 5th electron has to go in where there already is an electron on one of the 4 walls, so you end up like this. Now, to the question, does the pair of electrons have to show up on the top? The answer is no. It can really show up anywhere. Usually, this is where you have a bond. This is where you would have a bond. So if you have another atom and you're forming a bond, this is where the dot would be. And then the lone pair would be like that. Oxygen is in group 6, so it has 6 valence electrons. So we're going to draw the 6 electrons on the 4 walls. So we're going to put in our first electron here, second electron here, third electron here, 4th electron here. Our 5th electron goes here. And I could have put the 6th electron here, or I could put it here as I have shown here. Chlorine is in group 7. It has 7 valence electrons. So I'm going to put the 7 electrons, 4 walls. First electron goes here, second electron goes here, third electron goes here, 4th electron goes here, our 5th electron goes here, 6th electron goes here, our 7th electron goes here, and our last wall only has 1 electron and doesn't have an octet quite yet. So these are Lewis dot symbols. So anything in group 4 is going to have this electron symbol. So germanium is going to have the same electron symbol as here. Anything in group 5 is going to have the same symbol as shown here. So phosphorus is going to have the same Lewis symbol and so on. Sulfur is going to have the same Lewis symbol as this. So if you just change this to an S, then it is the Lewis symbol for sulfur. Fluorine is going to have the same symbol as chlorine. Oh, I forgot that I actually wrote down the group number. So carbon, group 4, nitrogen, group 5, oxygen, group 6, chlorine, group 7. Okay, so what about a Lewis dot structure? Well, there are rules on how you do Lewis dot structures. So here is the molecule methane. So how do you do Lewis dot structures? What you do is, number 1, you count the total number of valence electrons for all atoms in the Lewis dot structure. So here we have our Lewis dot structure. Carbon is in group 4, so it has 4 valence electrons. There are 4 hydrogens, and each of the hydrogens has 1 electron each. Why does each hydrogen have 1 electron each? Because hydrogen is in group 1. So it has 4 electrons from the hydrogen, has 4 electrons from the carbon. You add them together, you get a total of 8 electrons. So you added up the total number of valence electrons for all atoms in the Lewis dot structure. Next, you put 1 pair of electrons between each pair of atoms. And you want to put an octet around all atoms. The only exception is if you have a hydrogen. Hydrogen can only have a duet. It cannot have an octet. So hydrogen can only have a maximum of 2 electrons. Hydrogen is never going to have 8 electrons around it. If you put 8 electrons around the hydrogen, it is incorrect. So what did we do here? We put a pair of electrons between each pair of atoms. So a pair of electrons, pair of electrons. Let's see if everybody has an octet. So carbon has 1, 2, 3, 4, 5, 6, 7, 8. It has an octet. Carbon has an octet. What about the hydrogen? We do not want to have an octet around the hydrogen. Hydrogen can only have a duet. Does hydrogen have a duet? It has 2 electrons. Yes, it does. So we have now satisfied the octet or duet rule for our molecule methane. So what we're going to do is we're going to call this our trial structure. We're going to count all the electrons in the trial structure. If the total number of electrons equals the total number of valence electrons that you have available from your calculation that you did in number 1, so you said 8 valence electrons total, you are done. So we look at this trial structure, we count up the number of electrons. You got 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 electrons, we are done. The alternate way that you can count up the number of electrons, and I do this because if you just try to count individual dots, sometimes you miss a dot and you end up with an odd number or something like that, and sometimes you don't actually draw the dots, you actually draw a line for a pair of electrons. So I just usually count pairs of electrons. So I'd say 1, 2, 3, 4 electron pairs times 2 is 8 electrons. So that's the fast way to do it. So in this case, we're done. Our structure is the lowest dot structure that we need. If the number of electrons is not equal to the number of valence electrons from 1, then you add 1 multiple bond per extra pair of electrons, and you iteratively go back to 2. So you do this, you go back, put in a pair of electrons between each pair of atoms, put an octet around all the atoms, and so on, until, so after you put in your multiple bond, you have to rearrange the atoms around, because you can't just leave them there, because when you put in a multiple bond, you've changed the octet situation. So you have to go back, and then you count the number of electrons. If the number of valence electrons equals the number of electrons in your trial structure, you are done. If not, you come back down here again, you put in another multiple bond, and you keep doing that iteratively until you end up with the final correct structure, and you can say done. Okay, so here are a bunch of lowest dot structures for the molecule methane, ammonia, water, and chlorine. So here's our electron count for the methane. We already did the methane. 4 electrons because carbon is in group 4, hydrogen is in group 1, but there are 4 hydrogens. So that gives us a grand total of 8 electrons. Our ammonia, nitrogen is in group 5, hydrogen is in group 1. So 1 electron per each hydrogen, but there are 3 hydrogens, so 3 times 1 gives you 3. So 5 plus 3 gives you a grand total of 8 electrons. Our water, oxygen is in group 6. We have 2 hydrogens. Each of the hydrogens has an electron each, so that's 2 electrons per the hydrogen, giving us a grand total of 8 electrons. In our chlorine, chlorine is in group 7, so 7 electrons each. There are 2 chlorine atoms, so 2 times 7 gives you 14 total electrons. So that would be the number of valence electrons that you're expecting to get. Now, why are these the correct lowest dot structures? We already said this thing has 8 electrons, so it matches. What about this? We put a pair of electrons between each pair of atoms. We put an octet around all the atoms. Hydrogen cannot have an octet, it can only have a duet, so this thing has a duet. We count up the number of electrons, 1, 2, 3, 4. 4 times 2 gives you 8 electrons, matches up, we're done. We're looking at our oxygen. We put a pair of electrons between each pair of atoms. Oxygen and hydrogen gets a pair of electrons. Oxygen and hydrogen gets a pair of electrons. Oxygen must have an octet, so you need to have 1, 2, 3, 4 electron pairs or an octet around the oxygen. Okay, so everybody has an octet. Hydrogen cannot have an octet, it can only have a duet. We count up the number of total electrons, 1, 2, 3, 4. 4 times 2 is 8. We match up the total number of electrons that we expect from our valence electron count. All right, what about our chlorine? We put a pair of electrons between each pair of atoms. We put an octet around all the atoms. 1, 2, 3, 4. 8 electrons around the chlorine. 1, 2, 3, 4. 8 electrons around the other chlorine. So both chlorines have an octet. We count up the total number of electrons in my structure. 1, 2, 3, 4, 5, 6, 7. Oops, sorry. So this is why you want to count in pairs, because if you start counting little dots individually, you go wrong. 1, 2, 3, 4, 5, 6, 7. 2 times 7 is 14 electrons. I am done because I have the correct number of electrons in my structure as I expected from the valence electron count. What I often do when I ask people to do lowest dot structures is I will give you maybe half credit as much as half credit for just having the correct valence electron count. What I often do with Lewis dot structures is I will often give you choices of Lewis dot structures. So I'll give you this, and then I'll give you one that's totally wrong, and then you get to choose one or the other, and then maybe explain why the one that's incorrect is the incorrect structure. So that's generally the kind of question that I usually ask for Lewis dot structure. I don't usually ask people to give me the rules for doing Lewis dot structures. What I usually do is I ask people to come up with the Lewis dot structure. So here are some done Lewis dot structures where you've actually drawn a line for each pair of atoms between atoms. You're using a line for a pair of electrons between each pair of atoms. And then we're seeing lone pairs. So these things are non-bonding electrons. Why are they non-bonding? Because they're not between two atoms. They belong only to one atom. So this nitrogen has this pair of electrons. There's not like another atom over here that it's sharing its electrons with. These nitrogens are non-bonding because they're not between two atoms. They're also lone pair electrons because they are sitting there as lone pairs. Because they're sitting there as a pair and there's not something else attached to the other side. So lone pair electron, lone pair electron. I have 3 lone pair electrons on the chlorine. Non-bonding electrons are valence shell electrons. They are just not shared between atoms. So what happens when you have Lewis dot structure and multiple bonding? Well, what I said initially is that if you do the electron count and the electron count in your trial structure does not match the electron count in your number of valence electrons, then you have to go back and add multiple bonds. So these are some molecules that have multiple bonding. So here's my ethylene molecule. I have a double bond between those 2 carbons. Here's my formaldehyde molecule. I have to have a double bond between these 2 atoms here. Here's my formaldiamine, and we have a double bond between the carbon and the nitrogen. So when you share 2 pairs of electrons, it is known as a double bond. When you share 3 pairs of electrons, it is known as a triple bond. So all of these are double bonds between these pair of atoms. So in our ethylene molecule, our total number of electrons was 12. Why is that? Because carbon is in group 4, it has 4 electrons. Hydrogen is in group 1, it has 1 electron. There are 4 hydrogens in my structure. There are 2 carbons in my structure. So 2 times 4 is 8, 4 times 1 is 4. You add them together, you end up with a total of 12 electrons. So this matches this Lewis dot structure. Why is that? Because if I count the number of electron pairs, 1, 2, 3, 4, 5, 6. 6 times 2 is 12, or it matches the number of valence electrons. Now if you look at the individual electrons, what we did is between each pair of atoms, we put a pair of electrons, right? Each pair of atoms has a pair of electrons. And then between these 2 carbons, we actually have 4 electrons or 2 electron pairs. Why is that? Because if you don't, then you don't end up with the correct number of electrons for your trial structure. So you had to put in the multiple bond. So you have to iteratively go back to come up with this structure. Now, does this carbon have an octet? Well, it does, because you got 1, 2, 3, 4, 5, 6, 7, 8. So it counts all of the electrons that it is sharing. So this carbon has an octet, this carbon has an octet. So this is a correct structure. What about in my formaldehyde molecule? Well, in my formaldehyde, I've got 4 electrons from the carbon, 1 electron from the hydrogen. There are 2 hydrogens, and we get 6 electrons from the oxygen. So we add that all together, you get 12 electrons. So in my structure, do I have 12 electrons? I got 1, 2, 3, 4, 5, 6 electron pairs, 12 electrons. So this matches the number of electrons in my number of valence electrons count. This is once again a multiple bond. Does this carbon have an octet? Yes, it does, because it's got 1, 2, 3, 4, 5, 6, 7, 8 electrons. So this carbon has an octet. Does this oxygen have an octet? 1, 2, 3, 4, 5, 6, 7, 8. Yes, it does. 1, 2, 3, 4, 5, 6, 7, 8. Yes, it does. So in my formaldiamine, we're going to do the same sort of thing. So we're going to do the number of valence electrons count. Carbon is in group 4, hydrogen is in group 1, nitrogen is in group 5. There are 3 hydrogens, there's 1 carbon, and there's 1 nitrogen. Add everything together, you get 12 electrons. So does my structure have 12 electrons? 1, 2, 3, 4, 5, 6. 6 times 2 is 12. Yes, it does. It has the correct number of electrons. We are done. Now, does carbon have an octet? Yes, it does, because it's got 1, 2, 3, 4, 5, 6, 7, 8. So carbon has an octet. Does nitrogen have an octet? 1, 2, 3, 4, 5, 6, 7, 8. Yes, it does. So everybody has an octet except hydrogen, which can only have a duet. So we are done. So what about electronegativity and bond polarity? Well, if you have something like this is a totally nonpolar covalent bond. It's completely nonpolar. Why is that? Because hydrogen is exactly the same as hydrogen. So both of these hydrogens have the same electronegativity. So there is no polarity in the bond. The electrons don't spend more of its time attached to one hydrogen than it does to the other hydrogen. They are distributed evenly. What about this? Well, chlorine is more electronegative than carbon is. So the electrons actually spend more of its time attached to the chlorine than it does attached to the carbon. So this is a polar covalent bond. If you push the extreme of a polar covalent bond all the way to the end, then you get an ionic bond. In an ionic bond, the electron spends all of its time attached to one atom and none of its time attached to the other atom. So the ionic bond is the extreme variation of a polar covalent bond. So the bond with the electrons shared equally is a nonpolar covalent. Unequally is a polar covalent bond. Okay, so what about dipole moment? Dipole moment is defined as the amount of charge separation multiplied by the bond length. So in this bond, I've got a carbon-chlorine bond. Chlorine is more electronegative than carbon is. So I'm going to give it a partial positive charge on the chlorine. I'm going to give a partial negative charge on the chlorine atom. This is a dipole moment arrow. This has the positive end of the arrow where you have the partial positive charge. The point of the arrow is at the partial negative charge. And this is the symbol for the dipole moment. And you can always draw dipole moment arrows for any bond that is polar covalent. So does that mean that you actually have to look up electronegativity charts such as shown here? This is the Pauling electronegativity chart. So do you have to actually memorize numbers of electronegativity, or how do you decide where the polar covalent bond is? Well, what you do is you can refer to the electronegativity chart such as shown here. This is just a part of the periodic table. It just left off all the transition metals and it's left off some of the other things, but essentially this is the periodic table, just a part of the periodic table. So this is group 1, this is group 7. So all you have to really remember though is you don't actually have, nobody memorizes electronegativity charts. However, you do need to memorize this. Carbon and hydrogen, carbon at 2.5 and hydrogen at 2.2, have almost the same electronegativity. So when you look at carbon-hydrogen bonds, you are to consider them to be nonpolar. Even though they look like they're far away in the periodic table, you just treat them as if they have the same electronegativity. The other thing that you want to remember about electronegativity is the position where they show up in the periodic table determines electronegativity. So if you have an atom over here in group 7 as opposed to an atom in group 1, these are on opposite sides of the periodic table. Remember, that was the one that we were doing an ionic bond between lithium and chlorine. Opposite sides of the periodic table, also very different electronegativities, 1 versus 3.2 or 1 versus 4.0. So these are very different electronegativities. So the closer atoms are to each other in the periodic table, so nitrogen at 3.0, oxygen at 3.4, they are very close together in the periodic table. So they have very similar electronegativities. Do you memorize electronegativities? I really don't. All I memorize is that the fluorine is the most electronegative atom, and going away from the fluorine, you decrease electronegativity. Going down from the fluorine, you decrease electronegativity. So as you go down the periodic table, so sulfur has less electronegativity than oxygen does. As you go across the electronegativity table, 4 for the fluorine, 3.4 for the oxygen, so you decrease electronegativity as you go to the left of the periodic table. So all I remember is that the fluorine is the most electronegative element, and then whatever goes away from it is less electronegative, whatever goes away from it is less electronegative. So if I'm comparing phosphorus and sulfur, phosphorus is closer to the fluorine than, phosphorus and silicon. Phosphorus is closer to the fluorine than the silicon is, so phosphorus is more electronegative than silicon. So that's how I memorize electronegativities. And why would you have to memorize electronegativities? Because I will often not give you an electronegativity table, but I will ask you to come up with dipole moment arrows. So what about formal charge? So when you do a Lewis dot structure, you really should put the formal charge on the Lewis dot structure that you generate. So what is formal charge? Formal charge is the group number minus the number of bonding electrons minus half of the shared or bonding electrons. That is the definition of formal charge. But formal charge doesn't necessarily tell you where the actual charge on the molecule is. So you can write out a number. That doesn't necessarily mean that the molecule actually has the charge at the position where you wrote the charge. So in the molecule H3O plus, the number of electrons from the oxygen is 6. The number of electrons from the hydrogen, the number of, this isn't the electron count, this is the formal charge for the oxygen. Okay, so when you're looking at the formal charge for the oxygen, group number of oxygen is 6. The number of non-bonding or unpaired electrons is 2. See these 2 electrons? There are 2 electrons there. And then you're going to subtract off half of the bonding electrons. There's 1, 2, 3, 4, 5, 6. So I'm going to take the 6, divide by 2, so that gives me 3. So 6 minus 2 minus 3 gives me a grand total of +1. So that means the formal charge on that oxygen is +1. Is the formal charge actually experimentally located on the oxygen? Not necessarily, but you write it like that when you write out the Lewis dot structure. So here is my Lewis dot structure for NO+. So what is the formal charge on this nitrogen and what is the formal charge on that oxygen? So this is similar to the formal charge that we did for the other oxygen. So we have 6, this is the group number, minus the number of lone pairs. I got 2 lone pairs, minus half of the bonding electrons. So I got 1, 2, 3, 4, 5, 6. So 6 electrons in my triple bond. So 6 bonding electrons divided by 2 gives you 3. 6 minus 2 minus 3 gives you +1. So the formal charge on that oxygen is +1. What about the nitrogen? Nitrogen is in group 5. You subtract off the non-bonding electrons, the electrons that belong only to the nitrogen. So there are 2 of them. And then you subtract off half of the bonding electrons. So there's 1, 2, 3, 4, 5, 6. 6 divided by 2 is the total number that you put in for the shared electrons. So 5 minus 2 minus 3 gives you a formal charge of 0. So nitrogen has a formal charge of 0. So when you write out a Lewis dot structure, you should also write out the formal charge. Although, in general, I don't actually count off, like if you give me the correct Lewis dot structure, I'm not going to take off like all the points because you have the formal charge in the wrong place. But when you do a Lewis dot structure, you should actually show the formal charge as well.